Howdy, and welcome to the end of our look at double integrals, where we'll look at the change of variables. So this is the last thing that we need to do with double integrals. So after this, we'll begin looking at triple integrals. We'll move up an integral. But first, let's look at this because this is taking that idea of what we did with polar form and extending it to any transformation. So first off, we're going to introduce this by just considering a u substitution. So we know that when we have something like f of g of x times g prime of x dx evaluated from a to b, this is the same thing as evaluating f of u du from c to d, where d is equal to g of b, c is equal to g of a, and u is g of x. We've seen this plenty. We can also think of the reverse, and this is what we're going to be doing here, that we're transforming x coordinates to u coordinates by going the integral from a to b equals f of x dx, or times f of x dx. The integral of a of b from of f of x dx is equal to the integral from c to d of f of x of u times dx du times du. So we can kind of think of this in reverse as well. And this is the same idea, but these two things are the exact same idea, but in one of these, we're essentially taking x and making it a more complex expression, and up here, we're taking a complex expression and making it simpler. Generally, generally, there's room for both to happen depending on what there's room for either method depending on what you're working with. Most of what we do is going to be built around, most of what we do in this particular topic is going to be built around this idea. So, so far, this kind of holds with what we've covered with polar form. We said that if we had some double integral over a region of f of x y dA, which was in terms of x and y, we could turn this into a polar f of r cosine theta r sine theta r dA, but here dA is now in terms of r and theta. And this is over the region S, where S is now the polar version of my region. Here we're going to use R and S for our regions instead of D because it's going to be easier to notice when we've changed. So here we've essentially done exactly this type of substitution with the idea that x is r cosine theta, y is r sine theta. But here, this r dA needs to take the place of dx du times du. And in two dimensions, that's not as easy to establish just this essentially idea of like arithmetic canceling or like just or algebraic canceling rather. It's a little more it's a little more it's a little more structured than that, or a little more complex than that. But we'll get there. So first, let's look at a general idea of the transformations that are going on. We're actually essentially talking about creating something where x is equal to some function of uv and y is equal to some function of uv that comes from the transformation t for transformation of uv is equal to xy. So in other words, x is a function of u and v, not u being a function of x, which is why I say that this is more accurate to what we're going to be doing. In doing this, we're going to assume that our transformation is what's known as C1. C1 here just means that it's continuous it's continuous on like a first order derivative. So G and H have continuous first order partials. We'll get into why we need that. So what happens here is we haven't talked about actually shifting the variables of integration. So that's what's going to come. That's what we're going to do now. So this is just kind of the substitution we're going to make. So let's talk about how this actually changes things. So let's say that we're concerned with either integrating x squared over 25 plus y squared equals 1, or let's say that maybe this is our region, or this represents our R. So this would be something where we'd kind of feel like, oh yeah, I'll try polar form because it's an ellipse. But if instead we make the substitution x equals u over 2, y equals v over 10, our function becomes u over 2 squared divided by 25 plus y over 10 squared equals 1, which is u squared over 100 plus y squared over 100 equals 1, which is just a circle of radius 10. So here what happens is this ellipse, which is not always a pleasant equation to work with, becomes a circle, which is very pleasant to work with, which is not a problem, especially if we're going to eventually use polar form. Just R goes from 0 to 10, theta goes from 0 to 2 pi, job done, right? And circles are awesome. Circles are super easy with polar form. Um, so changing functions or changing boundaries really won't be too bad. It's going to be as simple as plugging things in. Now, in the case of boundaries, there might be something a little more we need to consider. So here, the idea is that we're going to describe the original region R in terms of u and v, but then we're going to need to use that new region to determine boundaries for the integral. So it's the same as changing the function, but now if we get new functions, we'll need to use those functions to determine boundaries so we can actually have an iterated integral. So we actually are able to solve things. So you'll see here, we're going to create a relatively easy example where we're not going to have a problem figuring out what the interval is. So let's say that we're looking at R being the region between xy equals 3, 3xy equals 10, y equals 6, and y equals 9. And we want to use the transformations x equals v over 2u, y equals u over 3. So here, if we plug these in, we're going to get new boundaries of v over 2u times u over 3 equals 3, which gives v equals 18. Everything else cancels. We get 3 times v over 2u times u over 3 equals 10, which is v equals 20. So v is between 18 and 20. We get u over 3 equals 6, so u is 18. We get u over 3 equals 9, so u is 27. So u is between 18 and 27. So what was sort of this banana shape, if you will, kind of, has now become a rectangle, which is much easier to deal with. So this is what's going on here. We're taking a complicated region and making it simple. It's important to note here that these boundaries should be defined by a one-to-one transformation. So if I go from these 4 boundaries into this, my transformations, these particular things, should be able to get me back. That things here, we want them to be one-to-one, meaning that essentially meaning that I have both a forward transformation and an inverse transformation that are both well-defined. So let's take a look at how that might be a problem. Because we absolutely have a situation, I can absolutely create a situation without too much trouble where this might happen, where we might need to pay a little closer attention. So unfortunately, going to have to make do with the whiteboard once again. But let's take a look at these boundaries. So it's going to be, we're going to look for the area inside these 4 boundaries. So the boundary x squared y equals 2. The boundary xy equals 2. The boundary, we'll use the boundary y equals 2, and the boundary y equals 8. Now here, This just describes a region in the first quadrant. You could absolutely solve this with a standard integral without a problem. You could rewrite this as x equals the square root of 2 over y, x equals 2 over y, going from y equals 2 to y equals 8, and you would just have a standard integral in Cartesian coordinates, which is certainly solvable based on based on just calculus 1 knowledge. Not a problem. But here we're going to use double integrals to do this, just to show that, just to show how it is that this works, and also to show that we're going to get something that we need to pay attention to here. And not only that, but we'll find an answer using double integrals, and then I would say, an exercise to the listener would be to go ahead and actually find the area encompassed by these four curves using calculus 1 knowledge, and make sure that your answer there matches what we get doing this through a double integral. And the reason we care about doing this through a double integral at all is because if I wanted the volume below a certain other surface that's just above this, that's just bound by this particular, let's call it parallelepiped, then now we have some sort of now we have an integrand that's not trivial. So now we might need to resolve that. But we'll, that's something that we'll certainly see in some of the examples later in this lecture. So first off, what we'll use is we are going to use we're going to use the same transformation that we use. We're going to use, actually, I'm going to change the transformation a little bit. We're going to use x equals v over 2u, and we're going to use y equals 2u squared. So if we look at x squared y equals 2, what we end up getting is we get v squared equals 4. And here you can see that this is true. Just, we get v squared over 4u squared times 2u squared equals 2. So v squared over 2 equals 2, v squared equals 4. Here, what we end up getting is vu equals 2. Here we get u squared equals 1. These are all supposed to be equal signs for the record. I just have mouse problems. Equals. And then finally plugging in here, we get 2u squared equals 8, or u squared equals 4. So what we might notice here is that these have a whole bunch of interesting issues. So u squared equals 1 and u squared equals 4. Obviously, these are going to be my boundaries for u. But do I want to go from -4 to or do I want to go from -2 to -1? Do I want to go from 1 to 2? Do I want to go from -2 to 1? Do I want to go from -1 to 2? Probably not those last two for relatively clear reasons. But do I want to use negatives or positives? And it's going to turn out that my choice for these will affect my choice for v. Because remember, ultimately, the actual region we started with, everything is positive. Everything is in the first quadrant. So if I make a choice for u where I say, hey, I want u to go from -2 to -1, well, then v, if u is negative, v needs to be -2. Otherwise, x won't be positive. So that means that if u is negative, v is going to have to be negative as well, which fits right here. Generally, when we work with roots, we are going to choose the principal root. So here, it stands to reason that it stands to reason that u is going to go from 1 to 2, and v is going to go from from 2 over u, right? Because v equals 2 over u here, to 2. And the reason that we know that the reason that we can tell that v is supposed to go from 2 over u to 2, not from 2 to 2 over u, is because we can just look at where u is. Obviously, for anything that u has in this interval, this is smaller. So this needs to be my lower boundary. So these are our boundaries. So what that means that we end up with here is we're going to end up having something we're going to end up having something like this. That's a terrible 2. All right, great. And there's not going to be any particular integrand because we're just looking for an area, so there's no volume that we need to pay attention to. So our integrand would normally be just dA. Now, this is an issue. This is, oops, let's make that A better. This is where we have our problem, right? Because we've changed our boundaries to be in terms of u. But now this is still in terms of x and y, or u and v rather. This is still in terms of x and y. So we need some way to resolve that. So let's return to the notes and we'll talk about figuring out how to handle our variable, how to actually handle our variables of integration, how to actually handle our differential. So essentially this is the turning dx into du portion of u substitution, except with a double integral. So let's move back over to the notes and we'll return to this example in a moment. All right. So let's discuss how to complete the change of variable here. So in the same way, in the same way that we need to use the change in u with respect to x for u substitution, we need to consider the change for my transformation from uv to xy. So here, let's use the directional derivative, because we need to figure out what the total change in my transformation, from my transformation, should be the change with respect to x, and the change with respect, it should be both the change with respect to x and the change with respect to y. So here we get that the partial t sub u is dx du, sorry, times I, right, plus dy du times j, or in the I direction, in the j direction. And then here, t sub v is dx dv I, dy d plus dy dv j, again, in the I direction and the j direction, in the cardinal directions. And what this does is this allows our change to be represented by the parallelogram formed by the cross product t sub u cross t sub v times delta u delta v. This is the way that our Riemann sum is going to be represented in terms of u and v instead of in terms of x and y. So here we deal with a cross product in the using determinants. So we do ijk, dx du, dy du 0, dx dv, dy dv 0 gives me dx du, dy du, dx dv, dy dv as a determinant times k, which for notation purposes and for the purposes of making things look a little bit cleaner, we're going to reverse the dy du and the dx dv so that my x's are in the, so that all of my x's are in the first row and all of my y's are in the second row, and my u's are in the first column, my v's are in the second column. So this isn't going to change the determinant in any way. So this creates dx du, dx dv, dy du, dy dv, and this is known as the Jacobian, which we write as the partial for xy, or the partial for essentially the partial dxy over duv, which is the determinant of dx du, dx dv, dy du, dy dv. And what this gives us is a final look at this gives us just a final look at what exactly is going on here. So this gives us that our dA was originally terms of dx and dy, but now that should be not a partial dA, that should be an absolute dA, my apologies. But now what this gives us is it gives us everything in terms of u and v. And what we have here is all we need to do is multiply by the absolute value. Notice that this is an absolute value. This isn't me mistakenly writing the determinant a second time. This is an absolute value. The absolute value of the Jacobian needs to be multiplied in. And that will be what allows us to change from dA to, in terms of x and y, to dA, which I've written dA bar, in terms of du and dv. Let's return to that first example I did, and then we'll run through a few more here. I've got 3 more examples to go through. Neat. But let's go to that first example I had on the marker on the whiteboard. So let's return to this. So this dA, it needs to be replaced with this. So I'm going to have to work over here. So it needs to be replaced with essentially, my apologies, dx du dx dv dy, that is the worst partial d ever, dy du dy dv. Let's try those 2 again, because that was appalling. That's totally a partial d. Don't at me, bro. Good enough. All right. So what is this exactly then? Well, dx du is going to be v over 2 ln of u. Or sorry, not that. Did the integral by mistake, not paying attention, doing too much with integrals in Calc. It's going to be negative v over 2 u squared. And then here, our next look is going to be dx dv, which is just going to be 1 over 2u. Not really a problem. The next thing we're going to deal with is going to be dy du. Dy du is just 4u. and then dy dv is just 0. So the determinant here is just going to be negative v over 2u squared times 0, which is 0, minus 4u times 1 over 2u, which is going to be negative 2. But keep in mind that we need this to be an absolute value, right? So this dA becomes the absolute value. Come on, get there. This is going to become kind of this absolute value of negative 2, right? So this just becomes 2. And then here, excuse me, and then here, we need to make sure that we do things in the right order. So here, this was with respect to v, so it needs to be 2 dv du. And now this shouldn't be a problem. Now we should be golden. Because what's going to happen here is I'm just going to go ahead and integrate. So we end up getting the integral from 2 over u to 2. So we get 2 times the integral from 1 to 2 of 2 minus 2 over u du. And then obviously this is going to end up being, I can factor out another 2 if I want. But this is going to end up being just 2 times, and now we just go, hey, 2u is just going to be 2u is just going to be 2 times 2 is 4 minus 2 times 1 is 2, so just 2. And then here this is going to be minus 2 ln of u, but that's just going to be minus 2 ln of 2. And the reason for that is that this ends up creating something where we say, oh, well, the other side is ln of 1, which is obviously 0. So here, what we get as a final answer is 4 minus 4 ln of 2. And you can justify, or you can check, that that is indeed going to be our final answer. That is indeed going to be essentially 4 minus ln of 16, if you want it to be super nice. That is indeed going to be our result, whether we've done it through this double integral or whether we've done it through just a single integral via calculus 1. So so that, that about covers everything that we need to concern ourselves with. So let's go ahead and jump back into the original notes. So we'll go and we'll take a look at we're actually going to skip example 1 because it's roughly the no, we'll do example 1. So we'll go ahead and take a quick look at this. I have an edit to make because I used the same thing here where I wasn't paying attention. So this is, not v over 2 ln u. This is This is very much just as before, because it's the same thing. This is very much negative v over 2u squared. It would be great if that would not be awful. Not going to matter to our solution in any way because this is just going to zero out, but worth being correct. Serves me right for doing this while also working through integrals and calculus. All right, so let's take a look at example 1 here. So let's complete this problem where we found that we were working with this general information. Let's complete it by actually finding the integral beneath z equals xy squared. And again, this is the same region. So we've already seen that 18 is less than equals v is less than or equal to 20. 18 is less than or equal to u is less than or equal to 27. So, you know, we already saw that we're working with this rectangle. So let's consider what xy squared is. Well, xy squared is v over 2u times u over 3 squared, which gives us uv over 18. So now we do dx du. Dx du is just going to be negative v over 2u squared. Dx dv is obviously just going to be 1 over 2u. Dy du is going to be 1 over 3, and dy dv is going to be 0. So here, negative v over 2u squared times 0 is 0. And then we have minus 1 over 2u times 1/3 is negative 1 over 6u. And again, here, what we end up getting then is this double integral over my interval for s of uv over 18 times the absolute value of negative 1 over 6u dA bar, which is du dv. And here, what we end up having happen is we say, all right, we end up getting just that this negative 1 over 6u just becomes 1 over 6u because we know that the range of values for u is positive. So we can drop the absolute value by dropping the negative. So we get the integral from 18 to 20, integral from 18 to 20 for v, integral of 18 to 27 for u. If you go back up here, you can remind yourself that that's the triangle we're working with, right? V was between 18 and 20, U was between 18 and 27. Oh, I wrote it again here, my bad. And so we get just essentially V over 108 du dv. Plug things in, and what we get is the integral from 18 to 20 of uv over 108, evaluated from 18 to 27. This is our evaluating for u, right? And what we get when we do that is v over 12. And then we just integrate that. Now we get v squared over 24, evaluated from 18 to 20, which is going to be 76 over 24, or 19/6. And there's our answer. Done. That is our volume. So let's look at another one. So here, we want to evaluate the double integral of x squared minus xy plus y squared dA over r, where r is going to be the inside of the ellipse x squared minus xy plus y squared equals 2. So, you know, essentially the idea here is that this is just going to be everything inside this ellipse. So we're going to start by looking at what happens when we transform x squared minus xy plus y squared. The wonderful thing here is my integrand and my region are the same function. So this is going to, you know, doing this transformation is going to pull double duty. So here, x squared is the same as root 2u or x is the same as root 2u minus root 2/3 v, y is the same as root 2u plus root 2/3 v. So we just square this to get x squared. We multiply the two together, which are this is a difference of two squares, essentially. So we just get 2u squared minus 2/3 v squared, and then here we square this, getting this. You can see me cancel down. You can see me cancel down terms that cancel, and ultimately this yields 2u squared plus 2v squared. So the boundary then is 2 equals 2u squared plus 2v squared. So in other words, 1 equals u squared plus v squared, and hey, that's just the circle. And this is exactly the circle, 0 less than equal to r less than equal to 1, and 0 less than equal to theta less than equal to 2 pi with u squared plus v squared equals r. But u squared plus v squared equals r means that, or equals r squared rather, means that this is just my actual new function is actually, if I switch to polar, just going to be 2r squared. But before we do all that switch to polar, we still need the Jacobian in term for du dv. So here, dx du is root 2, dx dv is negative root 2/3, dy du is root 2, dy dv is root 2/3, which is going to end up as a determinant being 4 over root 3, which is already positive. So this is what we get. This is kind of where we end up. And now is when we can make this switch to polar. So this 2 and this 4 over root 3, they need to stick around. But then what we get here is this u squared plus v squared can become 2r squared, and this du dv can become r dr d theta. One of your problems for homework tonight is actually going to be to use the Jacobian to prove that moving from xy to r theta forces this result. So rather than the geometric justification we used earlier, we're going to now show this with the Jacobian. So essentially, your Jacobian, your determinant should come out to r. But that's for your assignment tonight. That's right. We've essentially substituted twice. We've made a substitution we've changed variables in order to make our function nicer, and then we've changed variables again in order to make our function polar. And now here, once we're here, this is now easy, right? 2r squared, 2r cubed dr d theta goes to r to the 4th over, oh my god, so many errors in this. R to the 4th over 2, please. Evaluated from this is going to be, evaluated from 0 to 1. And then what's going to happen from here is we're going to say, like, all right, great, we got that done, and now we get to 4 over root 3 times theta, evaluated from 0 to 2 pi, is going to be 8 pi rather than 4 pi over root 3. And that's it. That's all we need to do. So we'll look at one more here. This example is from the online notes that we've seen used, that I've kind of referred you to before if you wanted kind of an extra source. So let's take a look at what happens here. Sometimes we want to find equations for boundaries before transforming. So Let's take a look at this integral. The double integral over, a region given by the triangle with vertices 0, 3, 4, 1, and 2, 6 of x plus 2y dA. And we're going to use the transformation x equals u minus v over 2, y equals 3u plus v plus 12 over 4. And so here's our r, right? Here's our original region. And what you can see is I'm going to define all of my boundary lines as actual functions here, so that I can plug kind of these transformations into these functions. And here, the reason we might need to do this is that, sure, I could immediately integrate this. This is doable. But I need two integrals no matter what. You're going to see that there's no way for me to split these in any way that doesn't force two integrals. But our transformation is going to allow us to make one, because here what's going to happen is if I plug in x equals u minus v over 2, if I plug in y equals 3u plus v over plus 12 over 4, we're going to get the transformations y equals 3 over 2x plus 3 is going to just become v equals 0. Y equals negative 1 over 2x plus 3 is just going to become u equals 0. And finally, y equals negative 5 over 2x plus 11 is going to become v equals 2u minus 8. So that generates this. It's still a triangle, but now it's a nice right triangle and very clearly can be done with only one integral. So u goes from 0 to 4, and v goes from 2u minus 8 to 0. Alternatively, we could have also written v going from negative 8 to 0 and u going from 0 to v over 2 plus 4. I chose to use the upper one here. The lower one is also completely appropriate and will yield the same answer. So once again, doing the Jacobian, remember that we want to use x equals u. We need dx du, which is going to be 1/2. We need dx dv, which is going to be negative 1/2. We need dy du, which is going to be 3/4. We need dy dv, which is going to be 1/4. Now we just go ahead and take the determinant. We get positive 1/2. It's positive, no need for the absolute value. So x plus 2y finally transforms into 2u plus 6. So what we get is the integral from 0 to 4. This is for u, right? And the integral from 2u minus 8 to 0, this is for v, of 2u plus 6 times 1/2, or u plus 3. So we integrate this, 0 to 4, u plus 3 times v, evaluated from 2u minus 8 to 0, gives us 2u squared minus 2u minus 24 du, integrated from 0 to 4. So we integrate this, 2u cubed over 3 minus u squared minus 24u, evaluate from 0 to 4, gives us an answer of 208 over 3. And this is how we do this. There is no more to discuss here. As a final note, and I'll flip back to my whiteboard and kind of show what I mean by this. Sometimes transforms aren't given, and we need to pick them. Things like, for example, choosing to convert to polar. No one, for the most part, you're not going to see a problem that just says convert to polar. Now go. You'll need to see like, oh wow, I'm working with a spiral or an ellipse or something that is obviously a conic section that can be better shown with polar or something like that. Then maybe I'll say like, oh well, I just go ahead and choose to convert this way. Other things we can do is just make conversions to make our life easier. So for example, we might have a double integral of that takes e to the x plus y over x minus y dA. And we might just choose that u equals x plus y and v equals x minus y. And then this kind of got cut off because scanning hates me apparently. But we could say x equals u plus v over 2, y equals u minus v over 2. You can just combine, just use elimination, substitution, whatever you want to do to, you know, to show that this is going to be true. But we can just use these transformations, and this will just, instead of being e to something disgusting here, it's just going to be e to the u over v. And then we deal with the rest of the transformation, and now it might be much easier to use. I'll kind of show a brief example of that right now. So let's just do one last example, and this will end the notes. So let's take a look at this. So we'll take a look at that is a horrific D. There we go, less horrific. All right, so we'll take a look at this integral. And so, you know, the integral of x plus 2y over x minus y dA. I don't know exactly why I need the parentheses there, but, you know, hey, whatever. So this is what we're working with. And here we're going to say that this is going to be in the this is going to be evaluated over the parallelogram bound by we'll say y equals x minus 2, y equals x minus 1. We'll do x plus 2y equals 0, and we'll do x plus, let's space those better, x plus 2y equals 2. So this is kind of this is what our A is. So what we might do is we might say, well, hey, what might be good choices for how I'm going to define these? And I might say, well, it seems like a great choice based on what's here and what's here to say that u is equal to x plus 2y, and to say that v is equal to x minus y. And this way, our integrand just becomes u over v, but this also works with our parallelogram. Because what's going to happen here is if we plug this stuff in, we just get u equals 2 right away, right? Right here. We get, or u equals 0, rather. U equals 2 below. Getting ahead of myself. And up here, x minus y, well, this is the same thing. If I move things around, I get x minus y equals 2 and x minus y equals 1. So up here, I get v equals 2, and I get v equals 1. So I get this for free, right? And now again, here I just need to go ahead and I need to be able to isolate x and y so that I'm able to find dx du. I'm able to find my partials dx du, dx dv, dy du, dy dv. So I just do that in just any algebraic way that you want. So x equals u. That's hello u. X equals u plus 2v over 2. None of those look like actual. None of those look like what? Really? Okay, fine. I guess we're. Guess I'll just do that then. None of this looks like what I want it to look like, but hey, whatever. Can't draw. And then we have that y is equal to u minus v over 3. And here, what that means is that we will get a Jacobian, which I'll put in blue. So blue. We get a Jacobian, which, for the record, by the way, we often write as J. We're going to get a Jacobian of, or more to the point, I guess we want the determinant of the Jacobian, because the Jacobian is just a matrix. But we'll get a determinant of du dx, or dx du rather, which is just 1/2, right? The v just goes away, the v just dies. Dx dv is just 1. Dy du is 1/3. And dy dv is negative 1/3. So here we get negative 1/6 minus 1/3 is negative 1/2. But since we need the absolute value of that, what we're going to end up with here is that this is going to turn into 1/2, right? Because, just negative 1/2 is obviously negative, so it needs to be positive. So our integral just becomes, and I've chosen to integrate with respect to u first, save my ln's for last, and this time I'm actually using ln correctly, unlike before when I was somehow getting it out of derivatives, because too much work with my other classes. What we have here is we have the integral from 1 to 2, and so this is our v, right? And the integral from 0 to 2, this is our u of u over v times 1/2. And then here, as I said, we're going to do our u's first and then our v. So what we end up getting here is this becomes the integral from 1 to 2. That's a 2. And this is going to be u squared over 4v, evaluated from 0 to 2. Which is just going to end up being 1 over v. And here, I think it goes without saying that this is just going to end up being ln of 2. Again, integral of 1 over v dv is just ln of v, and plug in 2 and 1, and you just get ln of 2. So there we go. That's it. So this is as much as you need to be doing. So this completes our look at double integrals. So after this, we'll begin looking at triple. So yeah, until next time.